So, do you want to learn how to time travel? How about shrinking the size of any object? With the shenanigans this guy came up with, you can do all of that and more. Results may vary in extraordinary conditions, such as things being really small. You are not responsible for any damage caused by the application of these methods.
All of this is possible with the magic of Einstein's theory of relativity. It is one of Einstein's most famous discoveries, and with good reason. It has revolutionized our understanding of the universe and has made possible countless and wonderful inventions, including the GPS. Relativity has two main types. There is special relativity and general relativity. Special relativity is far simpler, and thus we will be limiting our discussions to special relativity in this video. As a wise man once said, "There be dragons."
So, what makes special relativity special? Special relativity deals with inertial reference frames, in which an observer is not accelerating, whereas general relativity also describes situations involving non-inertial reference frames, such as a spaceship accelerating or falling toward the ground on Earth. Thus, special relativity is special because it describes or approximates a simpler reality, one in which nothing is accelerating. General relativity is to special relativity what special relativity is to classical mechanics. In more mundane circumstances, general relativity is not necessary to use over special relativity, since acceleration is relatively low. Special relativity is still extraordinarily useful, as it can also be used as an approximation for situations that are close to inertial reference frames.
All of special relativity can be derived from two very simple principles. These two principles are known as the postulates of special relativity. And these two simple postulates give way to all of the seemingly insane things that special relativity means, such as time travel and shrinking objects. The first principle is that the laws of physics are identical in all frames of reference, with no frames of reference preferred over any other. In other words, all observers are treated equally. The second postulate is that the speed of light is constant in all frames of reference for all observers. All relativistic equations can be derived from these postulates. The photon clock is a good way to visualize the relativistic equations and their derivations from the postulates. Say that we have a car with a photon clock inside of it. Let's say that the car is moving at some speed v relative to the ground. Now imagine that we shoot a photon from the light source. It travels up and hits the mirror, then travels back down to the light source. We then record how long it takes for that to happen with an extremely precise clock. Since distance equals rates times time, and we know that a photon travels at the speed of light, c, it's obvious that the time the photon takes to make this trip is 2d over c.
Additionally, expressing the distance d in terms of the time it takes the photon to make this trip for an observer moving with the car, we have this. This will come in handy in a moment.
But now consider what someone observing from the side of the road would see. By our postulates, we know that the speed of light must be c for the person on the ground as well. However, since the car is also moving relative to the observer, the photon travels a greater total distance.
Here we see this in action. As you can see, the photon travels a larger distance from this reference frame.
Using the Pythagorean theorem, we can derive an equation for this greater time interval.
We know from our postulates, the speed of light must always be c no matter the reference frame. Thus, in this reference frame, the time it takes for the photon to travel along its path is 2L over c. Then, using the Pythagorean theorem and our picture, we can derive an expression for L. Then, we can substitute in the value of d we found in the other reference frame. Notice how d must be the same in both reference frames, since the reference frames have no relative motion in the vertical direction. Finally, by combining our above equations and solving for delta t, we have an expression for the time it takes for the photon to travel along its path in this reference frame. Since v over c must be less than 1, the time of travel in this reference frame must be larger than the time in the first reference frame.
Further calculations can be done in this situation to derive the equations for length contraction and the velocity between two reference frames, but we will discuss such equations later.
Now, let's begin discussing some of the math involved with special relativity, so that you can calculate how distances, times, and velocities of objects can be warped in different inertial reference frames. An event is anything that occurs at a particular place in time. A spacetime coordinate can be assigned to any event. That is, in a particular reference frame, the position and time the event occurs at can be expressed in the form x, y, z, t. A coordinate transformation is where you switch from the position and time coordinates on one frame to that of another. Often this is from x, y, z, t to x prime, y prime, z prime, t prime. Classical mechanics has a very simple coordinate transformation called the Galilean transform. If you have a second reference frame moving at speed v in the x direction relative to the first, the equations governing the coordinate change under classical mechanics are x prime equals x minus vt, y prime equals y, z prime equals z, and t prime equals t. These equations you are no doubt familiar with from your prior study of mechanics. However, these equations are an oversimplification and are actually not accurate due to the nature of the two postulates. That is where a different set of transformations, called the Lorentz transformations, come into play.
When we're using the Lorentz transformation, what are we switching between? Well, when we use the coordinates, we are creating a frame of reference. S is x, y, z, t, or S prime is x prime, y prime, s, z prime, and t prime. And the Lorentz transformation is what we use to switch between those two frames.
Although the Lorentz equations come in many forms, a mere 4 of them are all that are needed to solve all sorts of problems involving special relativity. The 4 equations are given here. These relate the difference in x position between two events and the difference in time between those two events from the perspective of two different inertia reference frames. The strange letter you see in the equations is a gamma, which represents the Lorentz factor, which is given here. As we mentioned previously, we set up our reference frames so that the relative motion occurs in the x direction. Thus, between the two reference frames, the y and z coordinates of all events are the same.
So, how do we know which equation to use, or more generally, which frame is S and which is S prime? Ultimately, with how the equations are derived, it does not matter which values are placed in the part for S and S prime, so long as all the variables with the primes are substituted for the numbers in one reference frame, and all the variables without primes are substituted for the other reference frame.
When doing so, we must be careful to ensure that the correct signs are plugged in for v and delta x in accordance with how we set up the reference frames. As shown, S prime is moving at a speed v to the right relative to s. Thus, if in a problem, the reference frame we call S prime is instead moving to the left relative to s, we should plug in a negative value for the relative velocity v in the equations. Similarly, if we are considering two events A and then B in frame S, and B occurs to the left of A, then we must plug in a negative value for delta x, since our frame of reference has the positive x going to the right.
After this step, one can use algebra to reorganize the relevant equation to find the answer.
Additionally, the fact that the x and t coordinates change based on the frame of reference means that the velocities measured also must change based on the frame of reference. We can use the Lorentz equations to derive the relationship between the velocity of a given object as measured in one reference frame and the velocity of the object as measured in another reference frame. In our S prime reference frame, say we measure a particle that is traveling at velocity u prime. In classical mechanics, the velocity of the particle in frame S would simply be u equals u prime plus v. However, relativity changes things. Let's take the delta x equation and divide it by the delta t equation, where the two events we are discussing are measuring the position and time of an object at one moment, and then its position and time at another moment shortly after. This equation gives the average velocity of the object in the S frame. Rearranging, we get this. Now, in the limit, delta x over delta t becomes u, and delta x prime over delta t prime becomes u prime. Now, we have this, which is the relationship we were looking for. The implications of these equations are many. Directly from these equations, it can be shown how simultaneity, time, length, and as we've already shown, velocity, are all dependent on reference frames. Let's look at a few practice problems to illustrate some of the implications of the Lorentz equations and how to solve problems with them. Let's begin with the Planet of the Apes. The premise of the movie is that hibernating astronauts travel far into Earth's future, to a time when human civilization has been replaced by mere apes.
You maniacs! You blew it up! Oh, damn you! God damn you all to hell!
Considering the effects of special relativity, let's determine how far into the Earth's future the astronauts would travel if they slept for 120 years while traveling relative to the Earth with a speed of 0.999 c, first outward from Earth and then back again. Let's break the situation down into three events: A, B, and C. Let event A be the moment the spaceship leaves the Earth. Let event B be when the spaceship arrives at some point far away from the Earth 60 years later. Then let event C be when the spaceship returns back to Earth another 60 years later. Let's call the reference frame of the Earth S, and the reference frame of the spaceship S prime. Let's first consider events A and B. we know that relative to S prime, the spaceship's location is 0 meters. And we know that event B occurs 60 years after event A. Let's call when event A happens t prime equals 0 and mark these events on the chart accordingly. Now, let's use the appropriate equation relating delta t with delta t prime and delta x prime to solve for delta t for the S frame, the Earth. Through a similar process, we can find the delta t relative to frame S between events B and C. Thus, when the astronauts return, they will discover that 2,684 years has passed on Earth. That's the power of relativity. Let's do one more short practice problem to demonstrate how the Lorentz equations lead to the idea of length contraction. Say that a spaceship is measured to be 130 meters long from its own reference frame. Then, it races past a timing station at a speed of 0.74 c. Let's find the length of the spaceship as measured by the timing station. Let's consider the timing station to have frame of reference S and the spaceship to have frame of reference S prime. Let's call our two events A and B. A is the event of measuring one end of the spaceship, and B is the event of measuring the other end of the spaceship. From the spaceship's perspective, we know these events are separated by the length 130 meters, but we don't know the relationship between the time of these two events. Since relative to the spaceship, its ends are stationary, it doesn't matter when we measure the ends. However, from the timing station's perspective, it does matter when we measure the two ends of the spaceship. If we measure the ends at different times, the spaceship will have moved in between measuring one end and measuring the other, leading to an incorrect length. Thus, we know from the frame S these two events occur at the same time. We are trying to find the distance delta x by which these events are separated in this frame. To solve this, we choose this equation, since it relates our knowns, delta x prime, v, and delta t, with their unknown, delta x. Then, we plug in the values and solve the equation to find the length of the ship as measured by the timing station. Here we see that relative to the timing station, the length of the spaceship was measured to be only 87 meters, significantly less than before. This is once again the power of relativity.
To recap, special relativity is a more sophisticated model of mechanics and is especially important at high speeds. Its main postulates are that all laws of physics are the same in all frames of reference, and that no frame of reference is preferred over any other. And the other is that the speed of light is always c in all frames of reference for all observers. The Lorentz transformations are the equation to swap between different relativistic reference frames, and can be used to find the different positions in time coordinates and relative velocities. As suggested by the second postulate, all frames of reference are relative.